start, remember the exercise I asked you to think about yesterday. We want to derive the Lagrangian of quantum dynamics just using color symbols. So I am going to do it explicitly now. You will see it's really very, very simple. So I will do exactly the same I did yesterday to derive quantum electrodynamics. And the only difference is an algebraic difficulty. And is that the algebra of matrices is slightly more complicated than the algebra of numbers. Okay? But you are not afraid of algebraic problems. Okay? Therefore, that should be easy. So what we have? Our starting assumption is that there is one quark, any quark, one that exists in the universe, is a free particle. It has a spin 1/2 and mass m, and therefore it's described by the diagonal Lagrangian. But this quark appears in 3 different colors, of course with the same mass for all of them. So here there is an implicit identity in color space, three-dimensional identity that I will never write. So this Lagrangian has a symmetry because I can redefine the 3 colors with any arbitrary unitary matrix. So the quark field transforms into U times the quark field that mixes up the 3 colors. And the complex conjugate of the quark field will transform as U-bar, U-gamma. Since U-gamma is 1, which was a unitary matrices, nothing changes. Which means that you can choose any color basis you like. It's just a convention. But it's a convention provided that you use the same basis everywhere in the universe. Because I have a derivative, if I allow the parameters of my transformation to depend on the space-time coordinate, this is no longer a single element. And this goes against my prejudices concerning gravity. 2 different observers should be able to fix conventions in a completely independent way without changing the physics. Therefore, I will impose the Gates principle. And the Gates principle means if I want this to be a real symmetry, it should be symmetric when I allow the parameters of the transformation to depend on the space-time. And in order to do that, I need to change the derivative into a covariant derivative with a proper transformation. And it is here where the exercise becomes trivial or very complicated, but not very well. It's highly complicated depending on your notation. So the best thing to do is just use a notation as compact as possible. That's what I will do. I will be using the vector notation in color space, 3-dimensional. So I take a derivative, covariant derivative acting on the color vector Q. It can only be a normal derivative. Now I have made explicit identity in color space in 3 dimensions. And the only thing I can do is to add something with a Lorentz index. That will be the connection to make conventions independent of the space-time coordinate. I can put some coupling, okay, that is called TS, and a factor of I again, because the derivative will always carry a factor of I, so in this way, G mu will have a proper and be proper. And what I need that this covariant derivative transforms in the same way as the field. So it transforms as U derivative of U. If you think of the derivative as an operator, that means that what you need is that the operator's derivative transforms as U d U gamma. Because then when the operator derivative acts on the field transforms as U Q, U gamma U is 1, and therefore you get this transformation. So now everything is very simple. Because what you are saying is that once you do the transformation. This is the transform covariant derivative. This should be equal to u, the derivative before the transformation, u gamma. And now you just operate. This is u gamma, that is one derivative, plus u derivative of u gamma, plus u ds u gamma. This cancels with that, which is 1. And now you take the factors. The transform of G mu, calling G mu prime, is equal to u G mu u gamma plus this time with the appropriate factors. That's what I have. And if you look to this transformation, this is what you are familiar for classical electrodynamics. In classical electrodynamics, your transformation is just a phase. G mu is just the electromagnetic field. Things commute, u gamma is equal to 1, therefore you get the transform of the electromagnetic field, and the phase transformation is the electromagnetic field plus a term of this type. Instead of Gs, you have E. The difference here is that things don't commute. And since things don't commute, I really need to keep that. In addition, my field G mu, the blue field, if you want, is not really a field because it's a 3 times 3 matrix. This 3 times 3 matrix I can express in the basis of generators of my symmetry group. Therefore, it's a collection of fields times my basis of matrices in my 3 times 3 dimensional space. There are, in general, for SU1, there are n squared minus 1 generators. That is, for SU3, we have 3, the problem matrices. For SU3, we have 8. So, in our case, we have 8 rule fields associated with this gauge transformation. Okay, so what's the next step? You just take your Lagrangian and you change the normal derivative to the covariant derivative. And in this moment, you get an interaction term between the quark Q, QR, and your 8 rule fields. And the interaction is regulated by a constant, that's the strength of the interaction, times these color matrices, which are fixed. They are fixed by the item. So the interaction is an exchange of color between the quark fields and the gluon fields. Okay, with that, we solve one part of the problem. Now the second part is we need a kinetic term for these gluon fields. So we need to write something, a free Lagrangian if you want, for the gluon fields. It should be Lorentz invariant, it should be gauge invariant under this transformation. And it should be quadratic in the gluon fields. And of course, this transformation is slightly more involved with the transformation of electromagnetism. So the easiest thing to build the Lagrangian is look into that, and look into that especially. What do you need to write an invariant Lagrangian? Anything. You need to identify tensorial structures which are covariant. And once you have structures which are covariant, you know how they transform. Those are the building blocks. You can combine them into invariant objects. If you have a vector on the vector gives a scalar. Well, this is the covariant object that we know how we transform, u data. So I can define a commutator of 2 derivatives, and this will transform as u data. Now, if you put the derivative is this order here, the normal derivative is called mu. So with the factor minus I divided by the coupling strength I have put in front, this is the normal derivative mu g mu minus derivative mu g mu. So what in electromagnetics you call the field strength tensor. But the difference is that now you get a quadratic term which involves the commutator of this piece in one derivative with the same piece in the other derivatives. In electromagnetics, this is not there because the electromagnetic field commutes. Okay? But now we have it. And this transforms as U data. Of course, those are matrices. So this G mu, again, I can expand in my basis of 3 times 3 matrices. So I get 8 field strength tensors describing the gluons. The first 2 terms is exactly the same thing as in electromagnetics. The third one, the commutator of 2 matrices. You have 2 matrices, so you will give a constant factor of I, then F, A, B, C, the structure constant of your group, and another matrix. So you do correctly the projection with all the factors, so you get a term that contains 2 gluon fields, a coupling, and a structure constant. Now this object transforms as U data. Finally, as a matrix. Now it's very easy to find something that is Lorentz invariant. I take G mu, that's a Lorentz scalar. This is going to transform as U data. I take the trace, see the property of the trace. I can move the U data to the other side. U data is 1, so this is 1. If you expand these matrices in terms of fields, you know what the trace lambda A, lambda B is, the constant times delta IB. So that's pretty bad. And now you can compare it with electromagnetics. It's exactly the same structure that you have in electromagnetics, repeated 8 times, because you have 8 gluon fields. And with the difference, in electromagnetics, you don't have this type. But now, we cannot add a mass term for the same reasons that we could not add a mass term in electromagnetics, because an object like this is not invariant against transformation. Therefore, masses are absolutely forbidden for the gluons. So our 8 gluons are 8 C1 massless particles. And therefore, they generate interactions which are long range of electromagnetic interaction. Now we put everything together. Everything together is that's our Lagrangian. The kinetic term of the gluons plus our direct Lagrangian, but with the covariant derivative. And now it's worth to expand the Lagrangian in all its pieces and realize the structure it has, how nice it is. You have first the kinetic Lagrangian of the gluons. It's 8 times the kinetic term of the form. So there are 8 gluons. You have the free direct Lagrangian for your core. And now I have added as many flavors of course as you will have. Up, down, straight, jump, bottom, top. The covariant derivative contains that. So I get an interaction between the gluon field matrix, that is this times this with this factor of 2, with the quarks. So the gluon field interacts with the quarks with color alpha and beta. This contains a factor of the interaction strength G, and then it contains this matrix, this color matrix, which is completely fixed by the algebra of core. And so those are not free parameters, it's fixed. And I can put as many flavors of course as I will like, all of them will have the same interaction. And then, since my covariant, this G mu contains this piece, when I have G mu squared, I am going to have a piece that is this term times this term. So it will contain a factor of G, one structure constants, two gluon fields, and a third gluon field with a derivative. And this term squared will contain four gluon fields, G squared, and two factors of the structure constants. So I get interactions of three gluons in one space-time point, regulated by one factor of G and one factor of the structure constants, and interactions between four gluon fields in the same space-time point with a coupling G squared and two factors of the structure constants. So I get a very, very rich structure in my interaction, which is going to provide interesting phenomenological consequences. But the coupling is unique. There is a single coupling that is regulating everything. If you remember electromagnetism, in electromagnetism, you can add as many fragments as you want, and you can assign a different electric charge to each fragment, and nobody fixes the electric charges. So you can have as many different electric charges as you would like. The electric charges could be even irrational numbers. There is no ceiling in the electric system. Here it's impossible. There are no charges. Why there are no charges? Because if you go back here, you could try, for instance, to put here some factor Q, some color charge associated with the quark. You could change from one quark to another quark. That's what we did in electromagnetism. Then we put a factor of Q here, would be the charge of this quark, and the algebra will fix this factor of Q. This factor of Q will be whatever. But now, if you follow, the factor of Q will go always together with the gluon field. But now, you look into here, you have two gluon fields here. Each one will carry a factor of Q, so Q squared, and the algebra will require Q squared equal to Q, because it's a non-linear relation. And the only solution to Q squared equal to Q is either Q is 1, and you have a quark, something that interacts strongly, or Q is 0, and you have a lepton, that's not interact with gluons. There are no more possibilities, and the reason is that the group is non-abelian. And since it's non-abelian, you have this type of relation, which is a non-linear relation. Which means that the non-abelian gate theories are much, much powerful than the abelian ones. In electrodynamics, you have a single coupling associated with the photon, but then each fragment can have its own electric charge. In a non-abelian gate theory, this is impossible. You have in your Lagrangian a single universal coupling, which fixes everything. Another common, nowhere in this derivation I have used that n is equal to 3. The only thing I have used is that I have an SUN symmetry. So this Lagrangian is the Lagrangian of QCD, where the number of poles is equal to 3, but it's going to be also one part of the Lagrangian of the electroweak theory, where I will have an SUC. And I don't know if you have here about grand unification. Higher theories, for instance, there is a theory called SU5 that unifies strong and weak interactions. So this Lagrangian will be a part of that theory. The only difference is that the structure constants will be the structure constants of SU5. The electroweak theory will be the structure constants of SU2. Okay. Predictions of this Lagrangian. It contains a single coupling, so you just need a single measurement to fix the coupling. So let's look to simple phenomenology. I already showed you yesterday this event, remember? It's E plus E minus collide at the peak of the Z0 portion. So you arrange the beams so that they produce exactly 91 point something GeV. The Z0 decays in this point into a quark and an anti-quark. They go apart, each of them with an energy of 45.5 GeV. It's a huge energy. And they hadronize immediately because of confinement. So you find two jets of atoms. Each jet contains 20, 30, 40 different atoms. But the kinematics is a two of them. And I told you that 90% of the experimental events look real. How look the other events? Well, 9% of the events look like that. And you can immediately recognize that this is a three-body phase-space configuration. The Z0 has decayed into three very energetic particles that share the energy. Which ones are these particles? A quark and anti-quark. So one of the three jets is a gluon that has immediately atomized. Well, this gives 9% of the events. There is still a 1% of the events remaining. How they look like? They are more messy. They are more messy because now you start to share energy among more constituents, and the event becomes more noisy, but you can still recognize a four-jet configuration. So the Z0 has decayed into four different particles at short distances, which have abundance. Which are these four particles? You don't know. You have produced a QQ bar, and then these quarks have emitted gluons, so you have the four particles. Or maybe one of the quarks has emitted a gluon, and this gluon has split into another quark and another antiquark. Another possibility. And the two possibilities are behind this kind of events. Okay, so can you make sense of that? Right? Of course, the electroweak theory is going to fix this values. And QCD is going to fix the addition of the groups. Well, you just compare events. 90% of events are like this one, 9% of events are like this one, 1% of events are like this one. What is the difference from the QCD point of view? The electroweak production is exactly the same. The Z0 decays into a quark and another. But now, to emit a gluon, you pay a price, and this price is a factor of GS. Coupling of strong interaction. Probability is amplitude squared, so the price to have the three-body configuration is a factor of alpha s, the strong coupling. It's defined in exactly the same way as electromagnetic coupling. Alpha is G squared divided by 4 pi, alpha s is GS squared divided by 4 pi. So you need to pay the price of a factor of alpha s to generate 3 jets, to generate 4 jets. Now you have 2 different couplings of G squared at the level of the amplitude, that's G to the 4th level of probability, so alpha s squared. So the ratio between this and this gives you alpha x. The ratio between this and this gives you alpha x. The ratio between this and this gives you alpha s squared. Just counting the number of events, alpha s gets fixed. Is 0.12. And 0.12 is much larger than the electromagnetic coupling we are used to. So those are the strong interactions. But it's pretty perturbing. Okay. So the question is, now I go back to my Lagrangian. Everything is fixed. Because state symmetry has fixed the structure of the Lagrangian. I have three nice types of coupling. Okay? But all of them are fixed in terms of the strong coupling and color factors. And the strong coupling is already fixed as 0.12. How it is possible that a theory with only one parameter that is fixed, and in addition is a perturbative parameter, can explain nuclear physics? Of course, it explains the jets that we see at lab. It explains many other things, but when we are in high energy experiments, we know that strong interactions are perturbative, and we know how to compute with this Lagrangian perturbation theory. But once we go to nuclear physics, we have to find out. How is possible that this Lagrangian with a coupling just has a size of 0.12 confines and forces the quarks to be binding to the protons and neutrons, and atoms, and makes possible the formation of all the nuclear physics? Well, this is telling us that there is a fundamental difference between electrodynamics and chromodynamics. And the fundamental difference is that electrodynamics is a very successful theory at the classical level. And then you go to quantum corrections, and there are small corrections. Chromodynamics does not make any phenomenological sense at the classical level. Because at the classical level, it's a completely constrained theory, very elegant, it's beautiful. In 2 slides, we have derived a very rich Lagrangian, but this Lagrangian contains just one coupling, and with this coupling, it's impossible to explain nuclear physics. And you want to explain nuclear physics. What is going on here? This is a beautiful theory, but it's an implicitly quantum field theory. It's only when you go to the quantum level that the theory starts to make phenomenological sense. So I am not going to enter into the technicalities of real quantum field theory. I just will describe qualitatively what is going on. So let's start with electrodynamics. The photon couples to charge fermions. So in any electromagnetic line, any photon that propagates through space-time, the photon can make this type of bubble. It's called a loop, where you create, for instance, an electron and a positron, which then annihilate and again make the photon. This is called the self-energy of the photon. Okay? And it's a quantum effect. So now you imagine that you have two electric charges, one is here and the other is here, and the electromagnetic field goes from one to the other. But now the electromagnetic field means photons that are traveling through space-time from one point to the other. When these photons travel through space-time, they are creating these particle-antiparticle pairs all the time. And just from the classical point of view, this is a dipole. The photon has zero electric charge, but for a moment, when they create this pair. This is a negative electron, and this is a positive electron. So you have created a vacuum. Which means that the vacuum, you have two charges that see each other in the vacuum. From the quantum point of view, the vacuum is not empty. Because as the field is propagating, it's creating pairs of electron positons all the time. So all the space between the two charges is filled up by this kind of items. Therefore, a space-time from the point of view of electromagnetism is like a polarized dielectric medium. Because it's filled up with virtual electron-positon pairs, or in general, any type of charge particle that you put coupled with a photon will give a contribution. So now think about that in terms of classical electromagnetism. You don't need more to get an equation. So this is assume that this is generating the electromagnetic field, and this is your test particle that is feeling the effect of the field. If this particle is very far apart, there is a long distance between the two, there is a lot of space, and therefore there are a huge number of dipoles in the middle of the two charges. So what those dipoles do? They spin the electric charge. So this particle feels an electric charge that is much smaller than the true electric charge of this particle, because the dipoles are spinning. Now, if you take this particle and start approaching this one, as it approaches, there is less and less space in the middle, there are less and less dipoles, and therefore the spinning effect becomes weaker. Therefore, it will feel a larger electric charge. It will feel a stronger electromagnetic field. Which means that instead of alpha, the finite structure constant that you know, what is going to be relevant for physics is an effective value of alpha that depends on the distance. Q1 depends on the energy of the process. Large distances means small energy, small distances means large energy. Remember the quantum relation. So the electromagnetic coupling increases with the energy. This is a tiny effect. This is a quantum correction, and alpha is a very small thing. In fact, this effective alpha that depends on the energy, okay, to first ordering perturbation theory has more or less this form, okay, with a coefficient that is positive. Okay, and that is what explains this type of effect. And this is something that can be measured in the lab. Okay? In fact, it's the largest quantum correction to all the physics of lab, to all the weak tests and the set. The finite structure constant is the value of alpha at the electron mass scale. This is what you measure it. And it's known very, very, very precisely. Okay? This is the inverse, 1/130. But the value of the electromagnetic coupling at the Z pole, at energy more than mz, is 1/100.9. It's larger. It's not a huge effect, but since the separation of the scales between the Z mass and the electron mass is huge, this log is huge. Okay? And the size of this log compensates for the small value of alpha. It's clear? So, what happens in QCD? Well, in QCD it's more complicated because we have more interactions. So we have, of course, this kind of dipole. So now this will be a gluon, this will be a quark and d-quark pair, and we will get a similar effect, some scaling of the color interaction. But in QCD, we also have interactions between three gluons, and interactions between four gluons, so self-interactions. And these self-interactions generate the opposite effect. Instead of scaling the interaction, they throw interaction to large distances. In fact, we believe that they are not responsible for confinement. So when you compute any amplitude in QCD, so for instance here, one gluon exchange, we have two fermionic currents, we don't mind about the structure of currents. A gluon gets exchanged, you pay a factor alpha S divided by Q squared and make it transfer. And that will be your classical prediction, your logos over prediction. And now you start to compute quantum corrections. So you start to compute a series of corrections as powers of alpha S. And the main part of those quantum corrections you can reabsorb into an effective value of alpha S, which depends on the others. And this effective value of alpha S, it has also this form, but it happens that this coefficient, instead of being positive, is negative. And it's negative because it gets a positive contribution from the quark dipoles and a negative contribution from the gluon dipoles, let's say, which is much larger than the colors quantum numbers. There are no gluons and three colors of colors. So what happens is that in QCD, the interaction as a function of energy, the effective interaction behaves like that. There is a logarithmic scale. So here you are at 1 TeV energy, the largest energies we have been able to reach so far. This is 1 GeV. And this dependence is known nowadays to 5 orders in perturbation theory. So you do perturbation theory in powers of alpha S, and you have computed 5 terms in this perturbation theory, so it's known extremely well. And all these points are a way of showing experimental data. So with QCD, you can analyze a very large number of experimental observables at different energies and check that things work as you expect them to work. But one way to compare all those experiments is you do one experiment at given energy and use this experiment to fix alpha S at that energy. And you do the same for all the experiments, each one at the energy where it has been the experiment done, and now you plot the results of all these experiments between 1 GeV and 1 TeV as a comparison of values of alpha S. And the amazing thing is that all values of alpha S agree exactly with the prediction of QCD. So it's a very successful theory. We have derived the Lagrangian with 2 slides. Everything is fixed by the base principle. It only contains a single input, a single parameter, Ts. But then quantum effects are so rich that you are able to explain everything that we are able to measure and calculate in terms of a single value. And this theory is telling you that in the limit where the energy goes to infinity, the coupling goes to 0. This is called asymptotic freedom, because that means that quarks convert into free particles in the limit of infinity. And this is a property that comes from the non-abelian nature of the gates. Of course, there is a Nobel Prize for this fact that was known to the people that computed this thing for the first time. But then, as you go to lower and lower energies, you can see that the coupling grows. And is it clear that if you go below 1 GeV, you enter the non-particle frequency? And that's what you need to understand around physics and nuclear physics in particular. So this smells to confinement. What is the problem? We know very well how to do calculations in perturbation theory. We are not so good making calculations with a non-perturbable theory. Okay? So what we do at the moment is ADA models, or you do huge numerical simulations with supercomputers. This is called lattice field theory. And everything you're finally able to do with your numerical simulations can be an experiment. So we are convinced that this theory predicts confinement, predicts the right properties of the strong interaction. But so far, nobody has been able to prove confinement. So if you want an interesting but very difficult subject for doing the PhD, this is a completely open problem. Of course, maybe it's not the right subject because many people fail to try to solve the problem. It's not easy. But that means that we are convinced that this is the right theory of the strong interaction. But I could give you arguments why it is the only possible Gates theory to describe a strong interaction. Everything we know about the theory, if we are able to compute and measure, it's solved. And what remains to be done here is an engineering problem, if you want, that is solve quantum field theory and do it everything. Okay, of course I will not do that. What I will do now is to jump into the electroweak theory using what we know from a strong interaction. That means I will be using this Lagrangian. This Lagrangian, for QCD, I have used the Lagrangian with number of colors equal to 3. Okay, so just put n equal to 2, and that will be what I will use for electroweak. I don't know. Any question up to here? Okay, so let's jump to electroweak interactions. There is a difference between electromagnetism, QCD, and electroweak interaction. Formally, I'm going to do the same. It will be slightly more complicated, but it will be the same. But conceptually, there is a difference. In electromagnetism, I didn't make any assumption. If you remember, my assumption was the electron exists and has a spin on. And then I identify the phase symmetry of the direct Lagrangian and I got it. In the strong interaction, I did one assumption more. And it's there is a quark, it has a spin 1/2 mass m, and it has 3 colors. So it has a new degree of freedom called core. It's a very, very slight assumption, and from that I got the complete theory. In the electroweak theory, I need to do more assumptions, which means that I understand less what I am doing. Doing assumption means that I buy experimental problems. So I go to the experimental data and I see what the data tells me about the electroweak interactions. And the data tells me first that there are 3 factors. No idea whatsoever why there are 3 factors. So I will make today the right electroweak Lagrangian for a single family and then I will replicate it 3 times. But then experimental data tells me that these families, which contains 2 electrons and 2 quarks, have some very peculiar structure. Because what they tell me that, let's take for instance the electron and the electron neutrino, or the up quark and the down quark, that's the first family. They tell me that when I look into beta decay, for instance, that means something that is related to the charge W, only the left-handed polarizations of the fermions appear. The right-handed polarizations of the fermions don't interact with the W at all. Why this happens? I don't know. It's what we mentioned. So, the experiment tells us that in a beta decay, an electron transforms into a neutrino or vice versa, but always left-handed. In fact, we only know left-handed neutrinos. We have never seen right-handed neutrinos so far. Or when you get the transformation of a neutron into a proton or vice versa, what is going on is that an up quark transforms into a down quark or vice versa, but always with a left-handed polarization. And we can measure the polarization. So you just take the beta decay, you measure the angular distribution, and you immediately see that the polarization was left. So there is some relation between the electron left-handed and the neutrino left-handed, between the up quark left-handed and the down quark left-handed, when the right-handed components of those objects have nothing to do. So I need a theory that from the very beginning separates left-handed from right-handed. Those are different degrees of freedom. I have what we will call neutral currents, that means interactions of the photon or the Z, which are neutral particles. And those interactions conserve flavor. That means the photon of the Z, they couple to an electron and a positive. They couple to a muon and an anti-muon, a tau and an anti-tau. But they never couple to an electron and the anti-muon. So they couple to the particle and its anti-particle. You know that this is what happens in 3D. This is going to happen also with the Z0 position. And this is an experimental fact. And then the third property is universality. We don't understand why there are 3 families. The only thing we know is that the 3 families have exactly the same interactions. So the electromagnetic interactions of the electron, the muon, and the tau are exactly the same. The ones of the up, the charge, and the top are exactly the same. But the same happens with the interactions with the W, the interactions with the Z. Okay, so since it's universal, I will build my field theory for the weak interactions with one family, and then it will repeat 3 times because interactions. And then, since 10 years ago, we know that there is an additional interaction, which is not a Gauss interaction, because it's a scalar field called Higgs. And this differentiates between the families because the couplings are proportional to mass. Okay, so that's the new thing we know since 10 years. I will try tomorrow to explain exactly why this was predicted. And finally, it has been successful. Okay. So those are my inputs. So look to the inputs, especially this one, left-handed only. It means that from the very beginning, we are going to describe a theory where parity and charge conjugation are broken by 100%. So imagine that this is an electron, and the electron, imagine a classical rotation, so you can visualize this as the helicity of the electron. So only left-handed electrons interact with the W. Right-handed electrons don't interact with the W. So if I look to the electron through a mirror, and I look into the reflected electron, I will have a right-handed electron. And this right-handed electron, of course, it exists, but it does not interact with the W. So the physics of this object and the physics of this object for weak interaction is totally different. In fact, for positrons, it happens the opposite. Only right-handed positrons interact with the W, while left-handed positrons don't interact. Which means that if you start with a left-handed electron, it has an interaction with the W. If you apply a parity transformation, you go into a right-handed electron, so this does not work, this does not interact with the W. If you apply a charge conjugation, that means you change particles by antiparticles, you go from a left-handed electron into a left-handed positron, it does not interact with the W. But if you do the two discrete transformations, one after the other, either first P and second C or the opposite, you transform a left-handed electron into a right-handed positron. The interactions with the W of the right-handed positron are exactly the same as the interactions of the left-handed. So, experiment tells us that parity and charge conjugation in weak interactions are broken by 100%, while CP is still a constant. And that's true at least for one part. We will see tomorrow what happens with one part. Okay, those are the elements I need to prove the theory. So I want to make explicit that I am making assumptions, and some of the properties I will derive are because I am making these assumptions, but I need them. So what I will do is I take my left-handed doublet, either a quad doublet or a left doublet, let's call it field number 1. I take the field number 2 is the right-handed upward, field number 3 is the right-handed downward, and in the case of leptons, that will correspond to the right-handed neutrinos. They have put here in a different color because nobody knows whether it exists. And the right-handed electron. Okay. So I will derive the Lagrangian for fields number 1, 2, and 3, and at the end, I will change that to quarks or leptons depending on whatever we want. What will be my starting points? So I take these 3 fields, and I write the free Lagrangian for the 3 fields. So it's the direct Lagrangian. I am taking the fields to be massless. I will show in a moment why. And I just simply add the free Lagrangian of field number 1, field number 2, and field number 3. And now we look into the symmetries of this Lagrangian. Field number 1 is a doublet. So I can apply an SU2 transformation on this doublet that is redefining what I call electron or what I call neutrino. Let's forget about the electromagnetic interactions for a moment. Those are just the up and down. You remember isospin? Isospin just exchanges what is up and what is down, what is broken and what is neutral. So we have exactly the same. That will be a weak isospin. And clearly, if I change this field with U and this field with U dagger is 1. So weak isospin is an exact symmetry of this dagger. But this only affects field number 1. It's the only one that has a double state. While for the other fields, including field number 1, there is also a phase symmetry like in electromagnetism. I can change the phase of the field in a completely arbitrary way. So that's my symmetry transformation. Field number 1 transforms a phase transformation times an SU2 matrix. fields number 2 and 3, that's a phase transformation. I have put these factors, y1, 2, and 3, in the same way as I put electric charges in the electromagnets. So I will call that hypercharges, whatever you know. And I cannot put a charge related to the SE transformation because you can just see UCD, but in a non-abelian symmetry, there are no charges. Everything is fixed. Now you apply the Lagrange principle, so you change this derivative to a covariant derivative. Well, that's very easy. We have done it already. For fields number 2 and 3, it's just a covariant derivative of electromagnetism. So, a coupling, the hypercharge, and the equivalent of the electromagnetic field, we call mu. That's the gauge field associated with the phase transformation. And this covariant derivative transforms as the field itself. And the field strength, and the d mu transforms in this way. So everything is like electromagnetism, just changing E to G prime. That's the coupling associated with this U1 phase transformation. Instead of calling A to the field, I am calling it D. That's to keep a different notation. And instead of calling the charges Q, I am calling that Y. Okay. What about field number 1? Field number 1 has both a phase transformation and SE2 transformation. Therefore, the covariant derivative will contain the same term associated with the U1 transformation and the same term we have built for SU3 associated with the SE2 transformation. But now, instead of the gluon field that was 3 times 3 matrix, you will have a W field that is a 2 times 2 matrix. It contains 3 fields because there are 3 open matrices. So we will have W1, W2, W3. And this covariant derivative will transform as the field inside. It has the phase transformation, that's what this piece of the covariant derivative does for you, and it transforms as U left, it has the transformation, that's what this part of the transformation does for you, and the way this W hat field transforms is exactly the same transformation that we have there for the core. See that? So I'm just copying equations, there is nothing new. The only complication is this. I have 2 different symmetry groups. My equations get larger. And now I have a coupling for the SL2 left group that I am calling G, and a coupling for the U1 group that I am calling G prime. And in the U1 group, I have 3 hypercharges. What's next? Well, I take my Lagrangian, I change normal derivative to a covariant derivative. If I do that, then I have the normal derivative gives me the 3 Lagrangian I started with, and the rest of the derivative gives me interactions with the 3 W fields and with the D field, which are the equivalent of what we have seen previously with UV and UC. Then I need to add the kinetic terms. We know already the kinetic terms. The U1 field, it would be minus 1/4 d mu, where d mu is the normal field strength tensor of electromagnetism, which is invariant under the gauge transformation. While for the SU2 part, is the same Lagrangian we have written for QCD, but instead of being 3 times 3 matrices, they are 2 times 2 matrices. So this mu hat is just the commutator of 2 covariant derivatives times this factor. Is transformed as U dagger. And if you write it in terms of components, it's as the component has this structure. The normal F-mu term plus whatever comes from the commutator of 2 W hat matrices, but in this case the such a constants are just the Lagrangian symbols. That means that this Lagrangian is a kinetic term, but this contains a kinetic term that is the square of this factor, plus cubic interactions, that is this times this, plus quartic interactions that come from the square of this factor. They have exactly the same structure as the self-interaction of the groups, but now they will be self-interactions of the non-difference. The true kinetic term is here, is just that. Kinetic term of the U1 field plus 3 kinetic terms of the 3 W fields. So that's everything in the loop. So now, just a comment, why I put in my starting Lagrangian 0 masses for the formulas. Well, I did that because I was forced to do that. Remember my chirality projectors with the gamma phi factor? So each fermionic field can be split into the left-handed and right-handed part. Where left-handed and right-handed means whatever these projectors project. In the limit of very high energies, or 0 mass for the fermions, this corresponds to elicity. Elicity is not a good quantum number in general, this is always a good quantum number. So when I am calling left and right polarizations of the fermions, it's really this projection. And now you use the properties of this gamma 5 matrix, it's very easy to prove that gamma 5 can be commutes with any gamma. Imagine, for instance, that I gamma 0, gamma 1, gamma 2, gamma 3, and will be ready with gamma 0 in the lower. Now you take this gamma 0 and put it there. How can you do that? Remember, gamma mu is equals to mu. So gamma 0 and commutes with gamma 1, commutes with gamma 2, and commutes with gamma 3. So you need to jump 1, 2, 3 times. So this is minus pi, gamma 0, gamma 0, gamma 1, gamma 2, gamma 3. But now this is the same gamma 0. Gamma 0 does not compute with itself. This is just minus gamma 0. And you can do that with any of the matrix. So gamma 5 always will be commute. In addition, you can easily check that gamma 5 is a Hermitian matrix. And that's enough to see that if you take the direct Lagrangian and you split the fields into left-handed and right-handed components, the derivative term separates left and right, while the mass term mixes left. So if I build a theory where left and right have symmetry transformation properties, different transformation properties, I am saying that the left components have a nice symmetry that is not there for the right components. This is symmetric trivially, this is symmetric trivially, but this is not symmetric. So all my fermions should have exactly mass. And that's why I have built my Lagrangian starting from a massless free element. It's gauge symmetry that forces me to do that. And remember, we saw already in electrodynamics and thermodynamics that the gauge bosons are massless particles. Which means that from the very beginning, I know that I am going to fail, because in this theory, everybody is going to be massless. And of course, we know that particles in nature are massless. So that will be our problem for tomorrow. But okay, let's follow. We have this structure. So now you just analyze the different pieces of this Lagrangian. And this Lagrangian is extremely rich. It only contains two inputs, G and G prime. So everything is fixed by two coupling constants, two inputs. But it has a very rich structure because it has the structure of PVD plus the structure of UCD with the different. So let's start, for instance, from the covariant derivative. Forget about the true kinetic term and take just the interaction of the gauge fields which are there with the fermionic fields. And that's the structure you get from the covariant derivative. Field number one interacts with the W matrix. All fields interact with B mu, each one of them with its eigencharge. Okay, so that will be the equivalent to the electromagnetic interaction in electrodynamics. This will be the equivalent of the QCD interaction in thermodynamics. Now, let's look to this piece here. This means Pauli matrices with a factor of 2 times the 3W1, W2, W3 fields. You know the Pauli matrices, so you get this structure where you have W3 here and minus W3 here, because you have sigma 3, 1 minus 1. And here you get the combinations of sigma 1 and sigma 2 that give this, what I will call the W field, that is W1 plus IW2 divided by the square root of 2. And the complex conjugate of the field. And now you remember that this is up-down or neutrino electron. So you just look what are the interactions of the charge W field and those are the interactions. Okay. The G factor I have got it from here. I am looking to the off-diagonal elements, so up couples to down, or neutrino couples to electron. Everybody is left-handed. This field number 1 is the left-handed doublet. That's why I am getting 1 minus gamma 5 divided by 2. This is square root of 2, is this factor square root of 2 divided by 2. Okay? And I get the same exactly for quarks and leptons because I am doing the same. I am just calling field number 1 could be a quark, it could be a lepton. So you get this Lagrangian and you get extremely happy. And you get happy because this Lagrangian is exactly what you need to understand the derivative. So it works with 100% precision. When you start quantum corrections, that's the true Lagrangian you need for charge current interactions, and you get very clear. What are the fundamental properties of this Lagrangian? The interaction is left-handed. Why? Because I did it left-handed. I built the theory saying that field number 1 is left-handed. Because I knew it. Second, quarks and leptons have a universal interaction with the lepton. I get exactly the same Lagrangian with the same coupling. But that's because I have repeated the same history. Field number 1 can be a quark, can be a lepton. So what I have got is just what I put in from the very beginning. Is that clear? So I'm getting something very nice, I'm very happy, but I should be aware that I have started with some assumptions because I want to do that. Okay? But once I have got that, so I have got this nice interaction vectors between quarks and the W, between leptons and the W, now I can start making predictions because this Lagrangian contains more structure. I just got the interactions of the charge W, but I still have field W3 and field B mu. Two neutral fields, I would like them to be the Z and the photon. Is that possible? Let's start with the photon. Well, if I look here, W3 cannot be the photon. Because in field number 1, I have up and down. And I know they have different electron charges. So they cannot have the same coupling to the photon. But now I go here, and I also see that B mu cannot be the photon. Because field number 1 is also here. And the hypercharge number 1 is the same for up and down. They have different electric charges. They cannot have the same coupling to the field. But in addition, photons couple in exactly the same way to left-handed polarization and right-handed polarization. They don't make a difference. Which means the hypercharge 2, that is the right-handed up, should be equal to hypercharge 1, that contains the left-handed up. And hypercharge 3, that is the coupling of the right-handed down, should be equal to hypercharge 1, which is the coupling of the left-handed down. So no way I can get any of these two fields in the electromagnetic field. But you can still do one thing, and it's that I know that symmetry must be broken in some way, because I know that the Z and the W are massive quantities. Okay? So let's see if it is possible to find a combination of W3 and B, so a quantum superposition of these two fields, such that one of the two new fields is the photon, and then the other one will be the same. And it's a very simple exercise. You just put a mixing matrix with a parameter of the W, cosinus, sinus. You put this matrix here and there, so you change from the W3 and B to Z and photon, and you discover that mu has the QED interaction provided these two relations are satisfied. So G times the sinus of this mixing angle should be equal to E. G prime times cosinus of this mixing angle should be equal to E. And in addition, the hypercharges of the three fields should be equal to their electric charges minus the quantum number P3, the sigma 3 divided by 3. Minus 1/2 or plus 1/2, depending if it is the up component or the down component. It's a very simple algebraic exercise that I recommend you to do. You will need 5 minutes to do that, or more than that. But then you get a nice relation. Because what you get is that transforming your neutral kernel Lagrangian in this way, is changing the basis of your gauge fields, you get QED by 3 if you want, you are forced to get QED, and then whatever else remains is a Lagrangian of the fourth gauge field that we will call Z. And everything is fixed, so you get beautifully the structure of the Z couplings. So the Z has vector and axial couplings. It's not just 1 minus gamma 5. Why? Because field number 1 is left-handed, but fields number 2 and 3 are right-handed. Okay. Then you need to combine both structures, so what you get is a vector minus axial coupling, where the axial piece is just provided by x into the structure, so plus 1/2 or minus 1/2, and the vector part contains a dependence and explicit dependence with a modulus of the electric charge or the fermions, and that makes the difference between quarks and elements. But now, everything is a prediction. So, I repeat again, this was not a real prediction. It was built in from the very beginning, from my assumptions. But now, I really managed to get the electromagnetic interactions. I don't want to get more gauge fields than things I know that exist. And I get all the predictions for the new sets here. Okay. When this exercise was done, nobody knew whether the Z field was a physical field with physical activity. That was much before the discovery of the Z motion. So that was a prediction of field with all the couplings. One comment at this point, I am repeating the same thing for quarks and leptons. But for quarks, I put right-handed up and right-handed down, while for leptons, the equivalent of the right-handed up would be the right-handed neutrino. But I don't know whether it exists or not. Why we don't know whether it exists? Because nobody has seen any right-handed neutrino. Why anybody has seen a right-handed neutrino? Because with current experiment it's impossible. And it is impossible because it's a right-handed field, so it does not couple to the down. Okay? But when we have forced our neutral current Lagrangian to reproduce electromagnetism, we got this relation. For right-handed fields, this part is not there. They are singles, not doubles. So for right-handed fields, the electric charge are equal to their electric charges. And the electric charge of the neutrino is 0, so it does not interact with the photon. But the hypercharge of the right-handed neutrino is also 0, so it does not interact with the Z. Therefore, if a right-handed neutrino exists, it's an sterile particle that does not interact with anything. Like a phantom. And that's why usually right-handed neutrinos are not considered as part of what these are not, they are not needed to build the standard model. If they do exist, there should be some additional interaction with the sensitive. Of course, there is no problem putting the right-handed neutrino in the standard model. It's just a phantom. That's not many implications. Okay, what about self-interactions? Well, self-interactions are exactly the same self-interactions of QCD. The only difference is that instead of the structure constants of QCD, you have the lengths in the sequence. But when you specify all the components, they look much more messy, just because of this transformation. So if you write them in terms of W3 and B, B is not there. Only W3 appears in the self-interactions. Okay, so W1, W2, and W3 are the ones that appear in the self-interaction. And now you rewrite W3 as a function of Z and A with these mixing angles, and then you get this complicated structure where everything is fixed. And in this structure, you see that there is always a W plus W minus pair. So you cannot have a self-interaction of 4 photons. Okay, this does not exist in PV. Or 4 Zs, or 2 photons and 2 Zs, or things like that. And that's very easy to understand. The self-interactions come from W1, W2, and W3 with Levitz-Mittag tensors. So you can have at most one neutral field, W3, and then the other one should be W plus and W minus. So there is always necessary to have a W plus, W minus pair. Okay? So that's the Lagrangian. We have tested part of it, and whatever we have tested in Lagrangian is correct. So experiment with this. So we have built the Lagrangian, and I recommend you to take a piece of paper and do it by yourself, because you get a beautiful structure with many interaction terms. All of them fixed in terms of only 2 components, T and T prime. That at this level, with these relations, we have changed T and T prime by 2 other parameters, which are E and theta lambda. Which means that I can choose 2 parameters, one of them is electromagnetic coupling, the other one either I take theta W or I take something else. So there are only 2 parameters. The hypercharges have disappeared because they are fixed by the electric charges. That we know. So nobody knows where the electric charges come from, but since those electric charges are known, the hypercharges are fixed. So my theory only contains 2 parameters. And the theory is extremely successful. We have been doing experiments with this theory for the last 50 years, trying to prove the theory wrong, and whatever we have been able to measure, at least with the theoretical prediction, and at least with the theoretical prediction with very high accuracy. So the theory is correct. We know that this is the Lagrangian of the electroweak interaction, both electromagnetic and weak, in the energy regimes we have been exploring so far. And there is no doubt about that. However, we know that the theory is wrong. It gives the right predictions, but it has a very big problem. And the problem is related with that. We need masses, because we know that all fermions have a mass. We know that the W is a very heavy object. We know that the Z is a very heavy object, and the top, of course, is a very heavy object. However, this theory only contains massless photons. That's very good to understand why the photon is massless, and it's very good to understand why the gluons are massless. But for the rest of the objects, this is extremely bad. Okay, so we don't understand. If you were engineers instead of physicists, you would say, okay, who cares? You have done all your Galilean and algebraic relations because you like symmetry, everything is very beautiful, you have got the interactions. Okay? And you know that those interactions are the right ones, so you can be very proud. Okay? And this is a small detail. So we also know that masses are there, so just put the masses by hand, and that's it. Why do you want to predict everything? And engineers are right, in some sense, because I am talking about electro-weak interactions, weak interactions, very few ones. The couplings are very small, which means that just doing the first approximation in perturbation theory is good enough for many purposes. Okay? That's what I will call classical physics, classical field theory. So if I just compute things at the first order in perturbation theory, you can very satisfied. Because everything that you are able to predict explains the spectrum. That's why we know that the structure of the Lagrangian is a right symmetry. Moreover, if you are clever, you can always do predictions in a slightly different ways. You can even manage to make predictions with 1% accuracy. They work extremely well. But if you want to improve your accuracy, and improving your accuracy means compute the first quantum correction, you fail badly. Because everything you compute is infinite. Which means that if you introduce the masses by hand, what you are doing is spoiling the symmetry properties of the symmetry. The symmetry is not only case. But from the mathematical point of view, the theory is consistent because of the symmetry. In the moment you lose the symmetry, the theory is no longer mathematically consistent with the quantum theory. And any calculation you do at the quantum level just gives you infinity, which means you can get any number you want, and you completely lose relativity. Which means that you need gauge symmetry. So gauge symmetry gives you the right Lagrangian, but gauge symmetry tells you that the masses are zero, and this cannot be quite correct. So you need to do something, because you need the symmetry to be there and not to be there at the same time. But this is possible in physics, and it's called a spontaneous symmetry breaking. And I want you to understand what a spontaneous symmetry breaking is. So, in the few minutes that we have now, I will try to show what is this without any mathematics. So, just visualizing things. Before doing that, let me just make a comment that this you can understand why your theory does not work. There is a fundamental difference between a massless spin one object and a massive spin one object. You know from quantum mechanics that the spin one particles have depolarizations. Okay, you have the right theorem. Spin J is 2J plus 1 polarization. Okay, this is not true in general. You have done this proof in quantum mechanics in the rest frame. But if a particle has zero mass, the rest frame does not exist. Okay, so this fundamental property of quantum mechanics does not apply to particles with zero mass. If a particle travels to the speed of light, that's what a zero mass particle does, the only way in which we can measure the projection of the polarization of the particle is projecting the spin of the particle in the direction of movement. Okay, and that's called helicity of the particle. And for massless particles, the helicity is a Lorentz variable. In quantum physics, you are used to the fact that you have an electron with a spin pointing in a given direction. You do a rotation of your axis, and then this polarization of the electron transforms into a superposition of 2J plus 1. In this case, two different polarizations. Okay? Well, for a massless particle where the rest frame does not exist, you can do any Lorentz transformation on this helicity. Okay? It's invariant. It's invariant in the rotations, it's invariant in the push, which means that the helicity of the particle is a fundamental property of the particle. What you call a spin of the particle is just a modulus of the helicity. That's why it's possible that the left-handed neutrino exists, and you don't need a right-handed one. Because if the neutrino is left-handed and it has zero mass, it will always be left-handed. The same for the photon. But you know from classical electrodynamics that the electromagnetic waves have two polarizations. So the photon has two polarizations. Not three, not one. Why the photon has two polarizations? Because if I do a parity transformation of the helicity lambda, and the parity, the three momenta flip sign, the angular momenta does not flip sign, so you change from lambda to minus 1. So if a left-handed photon exists, a right-handed photon should exist because electromagnetic interactions are invariant on the particle. A similar argument can be applied to the W and to the Z, which means that our gauge bosons of the electroweak theory are spin-1 particles that have two polarizations on. 3 bosons times 2 polarizations gives 6 degrees of freedom. If I want massive spin-1 bosons, they have 3 polarizations. 3 times 3 is 9. I am missing 3 degrees. So the only way to provide masses to the W and to the Z is adding to the Lagrangian 3 additional degrees of freedom. 3 additional phase. Okay? Otherwise, those polarizations will not be there. And quantum field theories of massive spin-1 particles are not sustainably accessible to electrons. The electrons in the ultraviolet energy becomes very, very light. So that's why to describe spin-1 massive particles, we really need text. Okay, so this is just an argument that you should keep in mind. You need to add to the Lagrangian something to have the 3 degrees of freedom. And you need to add that in a way that preserves gauge C. Okay, that's the mathematical thing. Let's go now to the it should be this one. Okay, so that's we have already seen. So we are very proud because we got all the interactions of our theory just from symmetry, and we only have 2 free parameters. Right? And we have an extremely rich phenomenology, which is correct. But we have the problem with the masses, and this is a very serious problem. If you think a little bit, what will happen if the W and the Z were particles with 0 mass? Well, the first thing that it will happen is that the mass of the W is what regulates the nuclear reactions in the stars, particularly in the sun. These nuclear reactions happen at a given speed which is low because weak interactions are weak, and they are weak because the W is heavy. If the W was a massless particle, then weak interactions will not be weak. They will be much stronger. They will not be suppressed by the heavy mass, which means that the stars will consume much faster the nuclear fuel than they have. And our universe will just be different. Probably nowadays the universe will have already disappeared, because all the stars will be gone, and they will start burning too fast. If electrons didn't have mass, we know electron mass is tiny. We can put it to zero for most practical applications. But if the mass was really zero, they will be traveling to the speed of light. So atoms will not exist. Protons will not catch electrons or looking around. The up and down masses are tiny. You can neglect them for most practical applications. But it is crucial that the up mass is smaller than the down mass. Because if the opposite was true, then instead of the neutrons decaying into protons, that would be the protons decaying into neutrons. And then the nuclear physics that you know will be completely different. Because many nuclei will not be safe. So, masses are crucial. We need the masses from the mathematical point of view to make the theory self-consistent, but we also need the masses from the physical point of view. Because having or not having the masses changes completely physics. Let's look for a moment into that, so you can relax a little bit. I am sure that in summer you have seen this picture many times, so you see many birds in the sky. The sky has a perfect rotational symmetry, so all directions in the sky are the same. And birds are free to fly any direction they want. Because all directions are the same. But I am also sure that in some months of the year, you have seen that. Suddenly, all the birds fly into the same direction, exactly. All of them follow the first bird. Okay? And they even can make some dancing, changing directions, because in which direction they are flying doesn't really matter. Because all directions in the sky are the same, because they are rotations. But in the moment they travel in a particular direction, this direction is special. There is something peculiar in this direction that is different from all other directions. And what is peculiar is that the birds are traveling into this direction. So this is spontaneous symmetry breaking. And if you think a little bit, you will find many examples of spontaneous symmetry breaking in your real life. Okay, for instance, if I take this, I put this in the table like that. Okay? And I let this alone, in which direction it will fall? You don't know. Okay? It will fall in one direction, and only in one. So this direction is different from the other ones. So all directions are the same, but the physical system has broken the symmetry in a particular way. And symmetry is still there. Because since you are physicists, this looks too fancy. I can give you the same argument in more physical terms. Think about phenomena. That's something that solid crystal physicists know very well. You have a system of atoms, molecules, of electrons, The spins of the electrons point into a completely random direction. Each of the electrons points in a different direction. There is a lot of thermal movement. But if you start freezing the system, you will reach a critical temperature below which you see domains. And domains means that once the temperature is low enough so that the thermal energy is below the energy, characteristic energy of the spin-spin interaction, then the spin-spin interaction dominates and all these spins align. In which direction they align is arbitrary. You can have different domains in the same material, and in each domain, the electrons point into different directions. But within each of the domains, all electrons point into the same direction. So that's a spontaneous symmetry. Let me prove a theorem. That's going to be a very deep mathematical theorem, but I will prove it just with a donkey. Okay, so imagine that you have a hill which has this form. You are physicists, so this is the potential. And this potential looks funny because it has two minima instead of having one. And one is the normal situation you're used to. So here you have a donkey that likes symmetry, but is hungry. So if the donkey likes symmetry, it will be whiting and whiting because he cannot make his mind which carrot looks better because the two carrots are identical. But you are sure that at some point he will give up symmetry and will take one carrot. Okay? So the donkey has broken the system. So you will say that now the donkey is telling you that this is the true fundamental state. This state is identical to this one, but there is a difference. The donkey is there and it's not there. Okay, so it's the fundamental state, so it can take him up. But at some point, the donkey will become hungry again, and the donkey will remember that there is another carrot in the other side. Okay? So he will try to go to the carrot. But in order to reach the carrot, he needs to climb the hill. So he needs to spend energy. So from the quantum mechanics point of view, the donkey going up into this direction is a heavy excitation of the potential. It has mass. There is a massive excitation. You need to carry your own mass, the donkey is heavy, so you need to spend energy. Okay, and the donkey is hungry, but it's also lazy. So it comes time. And now, if you look to the donkey is smiling. And it is smiling because the donkey knows something that maybe you didn't realize yet. And what you didn't realize yet is that I am drawing a potential in the screen, so that needs 2 dimensions, but the physical world has 3 dimensions. And if the physical world has 3 dimensions, instead of 2 separated minima, vacuum, you have an infinite number, a beautiful valley, circular valley, okay, with an infinite number of the states of minimum energy that are identical. Okay, so it's a perfect rotational symmetry, a U1 symmetry. And in this beautiful valley, the donkey has as many carrots as he wants, because he can travel in this direction along the valley without spending any energy. So this excitation, so the donkey has declared that to be the minimum energy state, the vacuum. Okay? The excitations around this direction correspond to massive excitations. The excitations along this direction correspond to massless excitations because you don't need any energy to jump from one possible vacuum to the next possible vacuum. Those excitations of zero mass are called Nambu-Goldstone bosons. They appear in many physical systems. It appears that this is just a cartoon, something funny, but this is so important that Nambu won the Nobel Prize just for this discovery. Because the applications of this Nambu-Goldstone theory to many physical systems, both in particle physics and condensed matter, for instance, have very, very deep implications. So now you will answer the question, okay, my problem was that everybody was massless. I have discovered a way of generating more massless particles, so I am making the problem worse. Okay. Why I am happy with this theorem? Well, the theorem was proved. You can prove it completely within the quantum field theory framework. Okay. Not many people put attention to condensed matter people were using already this theorem. Particle physicists were not using too much this theorem. And suddenly, this collection of people in three different independent groups, they realized something. It was just a mathematical exercise without application to any kind of physical system. And what they realized is that if they take a Gates theory, typically they were taking a U1 Gates theory, Electromagnetism. To this theory, you add the donkey potential. So in the theory, you have a U1 symmetry, so you add a potential with this U1 symmetry, and you do it in the proper way. Your Goldstone excitation is 1 degree of freedom that you have added. It's a Goldstone in the direction of your symmetry, the U1 symmetry. So the combination of your Goldstone excitation and the Gates field behaves as a massive Gates field. And you didn't break the symmetry at any point, because all your Lagrangian symmetry. It's just that the properties of this combination, so that's the additional degree of freedom that you are missing, are equivalent to a massive field. The second excitation, going up the hill, nobody put attention into it. In fact, some of these people even didn't mention this second excitation because you were looking to this problem. Okay? To make a mathematically consistent way of adding a third degree of freedom into Maxwell. So this is called nowadays the Higgs field, just because this guy wrote the field in some equation. Okay? He wrote the field and forgot about the equation because that was not important. Okay? And that was just a mathematical exercise that nobody really put attention at the beginning. So you invent a new field that you don't have any notice in the physical reality about this field, and with that you solve a mathematical problem. There were only two persons that a few years later put their attention into that, were Weinberg and Salam. And what they did was to implement this exercise not into a mathematical field theory that was quite irrelevant, we don't need masses and electromagnetism, but they implemented this idea into the theory of Glashow that was the SU2 left and SU1 theory that we have seen. Okay. And what they found was what we nowadays call the standard model. They did that in, I think it was the 70s. Okay. The theory was so successful that in 79 they already got the Nobel Prize. It was clear that the theory was correct. However, all the theory that they developed was based on adding that by hand and saying that there is a new interaction, a new field of forces, that is the Higgs field, that nobody knew about. And for about 50 years, we have been building experiments to test this theory, our successful experiments, realizing that the theory was correct, but we were missing this new interaction. That's why the Higgs discovery was solved. Okay? So tomorrow we will look into that, but we will look into that not with cartoons, but with real mathematical equations to see how it works. Okay, let's stop here. Any question at this point? Things are clear, they are obscure. At least the Boston program is clear what the idea is. Think about it and we discuss it.